Hello students, in this video I'm going to discuss about common mode feedback circuits. So this circuit is basically intended for fully differential op-amp circuits. So this will be using only for this type of circuits. And so what I really mean by this fully differential circuits, it is a circuit where the outputs are in general taken differentially. So first let me review about single-ended op-amp configurations first, and from there we will try to derive some kind of motivation towards the design of fully differential circuits. Later on we'll be talking about some of the difficulties in defining the output common mode voltage values for differential or fully differential op-amp circuits. So, and finally at the end we'll try to ratify this particular issue, that is the difficulty problem, with what is termed as common mode feedback amplifier. So now let us consider a simple PMOS differential input with a single-ended. So here, as I stated, it's a single-ended configuration where I have a mirror load in order to copy the current that is flowing in the other branch to the output node. Yeah. So now let me just try to recollect what we have seen before. What we know is when we apply some kind of differential input across the gates of M1 and M2, what happens is there will be a small signal current that creates across M1 and M2 in opposite phase. So the current actually gets created like this, and this current has to flow from somewhere, right? So which is basically from the output. It just travels in, flows like this, and then comes back, and then steps down like this and goes all the way to the ground, and then it gets fed back like this. And again, when there is a current that is flowing through this diode connection, obviously it also creates a current through the drain of M4, which would again gets connected something like this. So you could able to see like almost 4 transistors, 2 or basically there's M1 and M2, which is nothing but a differential input device, along with the M3 and M4, which are termed as active load, or basically these are a simple current mirror load. Okay, so you get able to see that there are 4 transistors that are participating in this particular signal flow. And since because the current that flows through the diode connected M3 transistor, where this configuration, that is this diode connection, has a very large capacitance value, so which is nothing but it's a mirror capacitance, and since because the signal travels through this particular path, and in this particular path we have a very large capacitance, which is known as a mirror capacitance, it introduces a kind of a dominant pole in our system transfer function. So between V out and our V in, it creates a dominant pole, and that in turn reduces the bandwidth of the circuit. So this we have already seen. So there is a reduction in the bandwidth when we go for a single-ended op-amp configuration. Now let me try to have the same kind of discussion over a fully differential op-amp circuit. So this is a circuit that we have, and clearly it indicates that the outputs are taken differentially across VO1 and VO2. Now when we apply a differential input across the gate and this gate of M1 and M2, what happens is the current basically starts from this output node, basically from here, and then it flows like this. And then since because the current through M1 will be in opposite phase, it comes out something like this, and then it goes and then it reaches back. So it creates a kind of loop, something like this. And clearly this picture, the one that I have drawn in red, indicates that the small signal current will flow only across this M1 and M2 transistor, which are nothing but the same differential pair device. So it only flows across the differential pair device, and they never flow across these M3 and M4, which are acting as a kind of active load devices for us. Now Since because only two transistors participate in this small signal operation, this circuit are used in high frequencies or high speed differential amplifiers. And also the circuit that we have drawn, it's a pretty simple configuration. There is no much difficulty in doing this because we want an identical system across both these branches. So even as far as the design perspective is concerned, the circuit is very simple. But on the other hand, the biasing voltages like VB1 and VB2 has some so these two potentials creates a kind of biasing problem. So what is that problem? It's basically because both VB1 and VB2 tries to create a kind of DC current. So in the case of AM5, the VB1 creates, let us assume that the current I0. And again, this bias voltage VB2 creates a kind of current which is supposed to be equal to I0 by 2 and I0 by 2 across M3 and M4 transistors. Thus the choice of VB1 and VB2 has to ensure the DC currents like I0 and I0 by 2 to be exactly equal, like, which means like, so instead of writing like this, I can write it something like this. That is ID5 supposed to be equal to that of twice that of ID3, 4. So this is a major thing, like the choice of these two things has to ensure that this type of current flows, and also it also has to ensure that all the devices or all the transistors are in saturation region. In general, the value of VB1 and VB2 have to be matched to such a degree that the output voltages, that the average output voltages or is somewhere in between, half the way between the supply voltage. So what I really mean is, like, the DC component at these voltages VO1 and VO2 has to hang around somewhere equal to VDD by 2, and so that in turn ensures that all of the transistors in the circuit are in saturation, and also having this DC condition will ensure a very large swing at the output node. Let us consider a simple case. Assume that the gain from this point, that is from the node VB2 to the output, either it could be VO1 and VO2. Let us assume that there is a gain between these two nodes, and assume that this gain is around, we'll take a different color. So the gain between those VO and VB, let us assume that it is somewhere around 50. Now, and even we assume that these voltages VB1 and VB2 were being selected in such a way that I satisfy these conditions that I've stated here. But now, because of some reason, let us assume that the value of VB2 has got increased, say for example, from the nominal value, it has got increased, let us go with something around 20 millivolt. So what would happen to the output in that case? We know we want this output common mode voltage to be around half the value of VDD, in a sense like half the supply voltage, and this sudden change or due to any change in this value of VB2, the output voltage which was previously hanging around VDD by 2 has got now reduced by a voltage of 1 volt. So this is nothing but this 1 volt is derived by just multiplying the change in the supply VB2 multiplied by the gain from the node VB2 to this particular node. So that is how we get this 1 volt reduction in the output signal. So why did this reduction happen? Why it has not got increased, or the other way around? Why it couldn't able to stay with VDD by 2? We know that if the value of VB2 has got raised, what happens is the value of VGS across the M3 as well as the M4 would get increased, and due to which the current that was flowing across ID5, which was termed as I0, and whereas the current that we expect here to be I0 by 2, but this time, since because the value of this VGS where right now has got increased, what happens is the current ID3 would be greater than the value of this I0 by 2. This mismatch in the current, that is the mismatch between this ID3, okay, I'll write it here, the mismatch between the ID3 and the nominal current I0 by 2, this mismatch current would generally flow out of this path. Okay, and now what is this ZL that I've represented here as well as in the previous circuit? This ZL is nothing but it's nothing but the output resistance which I just generated here. So in this case, the output resistance is basically RO2 in parallel with RO4. Even in this case, it is going to be the same, which is going to be like RO1 in parallel with our RO3 transistor. Yeah. So now this mismatch in current has to flow in order to satisfy the Kirchhoff's law, should flow out of this branch. I think it should flow, or yeah, it has to flow inside. It is not flowing out because this component requires more current than the incoming current components. So in general, if this value is fixed, okay, now if this value is fixed to VDD by 2, and now due to the current that is being drawn from this particular part, it lowers this potential drop because there is a certain amount of current that flows across this ZL, and this creates a kind of reduction in the output voltage from the nominal value, which was VDD by 2 by 1 volt. So that is the reduction that has happened right now. Now, how does this 1 volt reduction creates a kind of issue in this circuit? Now, let us assume that this value that I've ended up is basically false. I think I need some space. I will just take off some of the these things so that it becomes clear. Yeah. So now this value, that is VDD by 2 minus 1 volt, let us assume that this volt has stepped down so much and this voltage basically appears across the drain and source of our M4. Now, when this VDS value falls across this M4 transistor, drain and source of our M4 transistor, and if it is lesser than the value of VOV of this M4, then what happens to the transistor M4 and M3? So basically, they will drive into triode region, right? So a reduction in this output voltage makes this transistor M3 as well as M4 to move into triode region, right? And this happens because of a very large resistance. Even for a small amount of current that flows here, it creates a larger DC drop across this resistance ZL. Now let us see what happens when the VB2, instead of being at a nominal value, has slightly got reduced down. Okay, let me go with the same value by which it has got reduced. So I just change this one to a negative, right? Now that this, so what happens here right now, just because I've reduced the value of VB2 from its nominal value, this in turn creates a small amount of VGS than compared to the nominal VGS that we had, and due to which the transistor M3 and M4 will draw a drain current that would be lesser than the value of I0 by 2. And again, there is a mismatch between the current that flows that is coming from the M1 and the current that is flowing inside our M2. Now, what happens to the mismatch in the current? This has to flow away into the resistance ZL. And when this current flows through this ZL, what happens is, in this case, it will shoot up this output node voltage from the nominal value, which was VDD by 2 plus 1 volt. So whatever the thing that I'm talking is all with respect to the common mode or under the DC or the quotient conditions, right? I'm not talking anything with respect to differential signals here right now. So now this has pushed, like basically this value has got raised, and how does it impact my circuit or the entire circuit? Now this value would basically constrain the voltage drop across this M1 drain and source as well as the M5 drain and source. What happens is, either of both these transistors would end up entering into triode region, or in sometimes if the shift is so large, then both the transistors would end up entering into triode. So that is what would happen. when the common mode voltage is shooted up. Controlling the value of VB1 and VB2 in an open loop system or in an open loop configuration, it becomes very difficult to control them, like to set to a particular value. As we know, like from control systems, we need some sort of negative feedback. I need a negative feedback system such that it tunes either the value of VB1 and or VB2. So let us go with VB2, okay, such that the VB2 is tuned to the required common mode voltage. So what I really mean is I need a common mode or a negative feedback system that tunes the value of VB2 and in a way that I can attain this common mode output voltage to the value that what we really require, or this negative feedback that we want to create is termed as common mode feedback amplifier. In this, the common mode term signifies that the amplifier have to work only on the common mode signal. So I'm trying to emphasize this particular word here. What I really mean is, like, I need to work only on this common mode signal when I try to create a kind of negative feedback to actually tune my VB2 to the required output voltage or the common mode output voltage here. And the second term, the feedback. So again, as I stated, what we really need was this negative feedback. Okay, and this negative feedback, I'm again trying to emphasize that this negative feedback has to work only on our common mode signal, not on any other type of signal. Let me emphasize the word feedback amplifier here. Let me consider a simple. So this is a negative sign, which has been wrongly marked. Op-amp that I have here is basically built using a single-ended op-amp circuit, right? And what we have done is, like, we have used this R1 and R2 to create a negative feedback loop around this particular network. Now, does this feedback can be called as a common mode feedback? The question. Its obvious answer would be no. I cannot call this as a kind of common mode feedback. So why it is not so called as? Basically, for a single-ended op-amp configuration, which I can just show it here. So this is a kind of simple single-ended configuration. So what was the common mode voltage at this particular Vout? We know, like, this node, when there is a DC current that flows across this, which I labeled as I0 here, and what I have across the drain of M1 and M2 are basically I0 by 2. And this current, when it flows through the diode connected, it creates some sort of VGS3. And the value that I have across this particular node is equal to just VGS3. And through contradiction, we have already proved that whatever the DC potential that we have here would be same as that of across the output node here. So in turn, the common mode voltage, that is, I think here I'll write it, the VOCM that we have across this node is basically given by VGS3, and this value is fixed the moment the current that flows here. So there is only one single control we have in this particular circuit, which is nothing but VV1. So based on the value of VV1, some current would flow, and that current in turn defines the value of VGS3, and this VGS3 will never change until otherwise we intentionally change our VB1. So what I really mean is there is no mismatch in this particular configuration. Now, so as I stated, the feedback that we have drawn is not a common mode feedback, and also this circuit doesn't require any common mode feedback, because the common mode signal VOCM is well defined. Okay, so it is well defined and it is not required, and we don't want any kind of feedback to redefine this common mode voltage over there. What this feedback basically can be called as then, because it is not called as a common mode feedback, then what is this feedback basically? What is the purpose it serves for us? So this feedback serves as a kind of differential mode feedback. And when we put this network around this op amp, it creates a differential gain whose value is given by minus R2 by R1, and this gain will work only on the differential mode signal. Now let me try to make things clear. So I'll just try to replace this single-ended op-amp symbol with actual circuit built using our MOS transistors. So now that I have replicated this structure with the actual circuit built using our MOS transistors here, and I have connected all this feedback networks to this circuit here. Yeah. So now, what is the common mode output voltage in this particular circuit? So let me change the color. Yeah. So what is the common mode component in this, or the DC component at the output voltage? So as we discussed before, it is nothing but when there is a current that flows across this M3 transistor, which we normally take it as I0 by 2, this creates a certain amount of VGS, and the value that we will end up to the output node would be defined as VDD minus this VGS3, 4. Okay, so it's basically a negative sign. It's changed here. Yeah, right. So this is the actual DC component that we have across the output node, and this serves as a kind of common mode signal. But anyhow, talking as a common mode signal with respect to single-ended is not a valid statement, but I just want to correlate the same statement with respect to our differential or fully differential circuit, where the context of talking about common mode is related to something known as DC. So that's why I'm just writing, but this is not the normal notion of stating. So what I really talk here is basically the DC parameter. Okay. So now coming back to our discussion, what I know is this Vin could be returned as something like the DC plus some AC signal, so which could be returned as VGS or VG, and then over that, over the DC, I just apply a small change in the input. So there is a kind of differential signal, right? Now, so out of that, this quantity signifies this particular, because this quantity signifies that the current that is drawn through this transistors would be equal to I0 by 2. And in turn, it in turn defines the DC component of the output node here, right? Now, how do I mimic this change? That is, whatever I apply over here, this VI, how does it induces the AC component onto my output node? So clearly, if the value of this, the DC gain of this entire circuit, if it is so large, then I can write the AC component, that is this, due to the AC input signal, the AC component at the output could be simply returned as minus R2 by R1 times that of VI. So this AC component is basically under the assumption that the gain or the open loop gain of this particular circuit is very, very high. Okay, so that is the reason why I could able to write this, and clearly this particular quantity signifies that this particular feedback loop that we have created around this R1 and R2 is related to the differential feedback component, and it is nowhere related to our common mode feedback network. Now let us see how to build the same type of negative feedback network around a fully differential circuit. For that, I just switch over here. So again, I change the symbol. It's a negative feedback. I wrongly wrote it here, but fine. So this is with respect to single end, whereas this one is a circuit where I have differential input as well as differential output, which is nothing but just termed as fully differential op-amp circuit, right? Yeah. So now, however, we had a kind of a network around this single-ended op-amp. Here again, we need a kind of feedback network around this. But the point here is they have to be in opposite phase with each other. So what we have done really is connected our R2 across the node or the negative terminal of the input node and connected back to the positive terminal. So they are actually opposite in phases. And similarly, the same thing happens when we connect this R2 resistance across the positive terminal at the input to the negative terminal at the output, thus creating a kind of negative feedback around this particular circuit. Now let me ask the question. So let me define the voltage VO, which could be written as the summation of two components VOCM plus VOD. Clearly, I know what is this value because this is nothing but the differential output voltage, and this particular circuit, that is the negative feedback around this particular op-amp, will define the value that I need across this VOD. Basically, this negative feedback, or I can just write it as the differential mode feedback circuit stabilizes the differential mode signal at the output, which is nothing but to a known value at the output to a known value. So what I really mean is the output of this or the VOD could be defined simply as something like R2 by R1 times that of my differential input. So again, if I am observing the outputs differentially, then I no need to apply VI by 2. It's just VI. Okay. If this is my VID, then just add it here. Yeah. So we know clearly this particular quantity, and this particular quantity is basically stabilized to this value due to this differential mode feedback circuit. But how about this guy? That is, let me choose a different color, vibrant color. Okay, so the green one. Okay, so how about this value? Not sure, right? In this particular case, is this answer, that is the not sure answer, is true for all type of fully differential op-amp circuits? Probably the answer would be no. Let me take a simple fully differential op-amp circuit, which is basically built with some resistive loads, something like this. Yeah, here. So this structure again has two output nodes, and these two output nodes are fully differential. Now, in this case, what is the common mode signal here? It is pretty clear. When we apply a common mode inputs, it draws some kind of current through them, and let us assume that the current drawn by this M3 is I0, and due to which I have I0 by 2 and I0 by 2 across the drains of M1 and M2, and due to which the common mode is clearly defined as VDD minus the drop across these resistance like RD1, 2, and the current that flows is basically I0 by 2. And this is the value that we would get under the quotient condition, right? Yeah. So now we also know that the differential gain of the circuit could be written as something like GM1, 2 times that of RD. Now, in order to increase the gain of the circuit, what we generally do is to try to increase the value of RD. But doing that will actually makes the common mode signal to go all the way down to the ground, which means that the value is not somewhere closer to the value of VDD by 2. Now again, so what I really mean is it creates a larger drop across, or the DC drop across the resistance RD, and that in turn lowers the value of common mode voltage lesser than the value of VDD by 2. So the other way of looking at this particular problem is creating such a large resistance in an IC is not a feasible thing, right? So the gain that we would end up out of this simple circuit will be very small, right? The differential gain will be always a lesser value due to the value of RD that we can put inside a chip. And if we put a larger value of RD somehow by utilizing most of our chip area, then what happens is the output common mode voltage will step down to a value that is far lesser than the value of VDD by 2. Now, in order to overcome this particular issue, what we wanted is, we want to replace this resistance RD with a kind of incremental resistance whose value is so large, but the drop across that incremental resistance supposed to be small. And we have already seen such kind of circuit, right? Which is nothing but a circuit. It's a simple PMOS structure. So this circuit has an incremental resistance when we look through the drain whose value is equal to R0. So this value is pretty large. But what is the voltage drop that is required across these two nodes? So that could be controlled basically through the value of VGS, and what is required across the drain and source is basically our VOV, right? So in this case, the value of the resistance is so high and the drop across the resistance is so less. But if we replace this resistance RD with such kind of current source load, and if the circuit is kept basically in a open loop configuration, then the chances of maintaining the currents ID, say for example the currents that is flowing here as ID 3,4 or something, right? So the current that is flowing across the drain of M3 and M4 to be exactly equal to that of ID 5 by 2, the chance of maintaining this particular relation is very small. The chance is very small. So chance of maintaining this relation is very small when we leave this under an open loop condition. So we need a common mode feedback to stabilize the output voltage to a known value. But this common mode feedback, that is Cmfb or common mode feedback amplifier, should work only on common mode signal component and should not disturb any differential mode component. So this is basically the main requirement of this common mode feedback network. So in order to make sure that we always maintain this particular relation between the top current source and the bottom current sources. So as a simple case, let me try to create a common mode feedback network around this particular structure. So I have to replace this RD with those current sources. So I just draw those structures, and we want this common mode feedback to work upon this VB2 or to maintain this VB2 so that the currents through them would be exactly half the current that flows across the, okay, let me label this one as M5, okay, across this M5 transistor, okay. And we want this feedback, the common mode feedback circuit, to adjust this VB2 so that it always maintains this relation. Now let me go for a simple case by shorting this node and then putting a kind of feedback, something like this. Now can this following feedback mechanism facilitates to establish the common mode feedback, or can this kind of feedback that I've drawn, can it work as a kind of common mode feedback circuit? So what would be the answer? The obvious answer would be yes. You might do not get surprised. It's yes. Then I need to know what is the output common mode voltage for this, right? Because if I state that the answer is yes, then I have to know a defined value of common mode output over here. So what is that value could be then? It's obvious right now the common mode output voltage could be returned as VDD minus VGS4. So is this kind of feedback, the one that I've drawn in the red color, would basically act as a kind of common mode feedback. So what happens to the differential mode signal at the output terminal? So that has dropped down to 0, right? Because we cannot get any kind of differential outputs here because both these nodes are shorted, and we cannot measure any kind of differential output components from these two nodes. So this has got down to 0. What is the requirement of the common mode feedback network? The requirement of the common mode feedback network is to work only on the common mode signal and should not work or should be intact with the differential mode signal. But this particular feedback that I've drawn basically fails to satisfy the second condition. So this condition is basically not satisfied by this particular network. So what we want is somehow some kind of common mode detector, as shown in this particular picture, which senses only the common mode of these output nodes, and then take that common mode out of that, because we know that VO1 and VO2 basically composed of both common mode as well as the differential modes. So this common mode detector should extract only the common mode information from these two nodes and then get us or try to filter out only the common mode voltage across it. A simple approach is to realize this common mode detector by making use of a simple resistive divider. So let us assume that I have the same VO1 and VO2 signals here, and we know that these two signals are basically composed of both the common mode as well as the differential mode signals in them. I want to extract only the common mode information out of this, and let me label these resistance whose value is same, okay, RCM and RCM. What is the information that I would get out of this particular midpoint of this particular resistance combination? Now, as we know, like this node will have a value which is equal to VOE1 plus VOE2 divided by 2. Now that when we try to combine these two quantities, what happens is the output of this node will be exactly equal to VOCM, right? So that is what we would end up. And the differential mode component would step down to 0 in this case. So now let me put this common mode detector across our fully differential circuit built using current sources. Now what happens here is just to add those two resistances and then feedback something like this. And I'm feeding the output of this, because the output of this is consisting of only the common mode signal, and just feeding that signal back to our transistor gates AM3 and AM4, and what we have is RCM and RCM. So before further analysis of this particular circuit, we know that this particular circuit is termed as common mode feedback amplifier. Now let me talk about this word amplifier. Where does this amplifier exist in this particular circuit? This amplifier is basically created through the resistive load RCM, and then it's been connected through our gate M3 and M4. So basically the M3 and M4 transistor acts as a kind of amplifier circuit with respect to common mode component, and the same M3 and M4 acts as a kind of load with respect to the differential mode component, right? Yeah. So coming back to our analysis, this particular circuit, that is the feedback network that we have drawn here, has two major issues. One is the inclusion of these resistances basically lowers our differential gain, because these resistances actually loads the output node. When I apply a differential input, the outputs are also differential, and due to which this node could be considered that they are connected to the ground. Now when I look across this node and look for the output impedance, what I have at the top is nothing but RO3, and when I look down it is RO1, and then I also have one more resistance in parallel to RO3 and RO1. And if this value is lesser than the comparable value of row 1 in parallel with row 2, then what happens is the gain that is produced out of this particular circuit would generally will be very small, right? So that is what the issue that we have. The inclusion of this RCM actually loads the differential component at the output. And the second issue that we have is that the output common mode voltage. So what is the output common mode voltage? So as we wrote at the beginning or in the previous page, the VOCM could be written as something like VDD minus VGS3, 4. And this output common mode level is not completely independent. So what I'm really stating here, that is the VOCM settles down to a value based on the current that is flowing across these drains of M3 and M4. And so in a word, the VOCM depends on the quotient condition of our transistor M3 and M4, and we cannot independently set the output common mode value, that is this one, to any particular value. Say for example, I cannot go and fix this one to VDD by 2. There is no freedom, there is no independent way for me to go and fix to a particular value. So this is basically a huge disadvantage because of this particular common mode feedback amplifier that we have drawn here. The solution could be by adding an extra, so we need a kind of extra amplifier circuit around the loop, and so that would be something like this. So what I really wanted is, I just try to take the common mode output, and then I'm just going to feed this common mode output to an amplifier where one of the terminal is fixed to the common mode value, whereas the other terminal of this particular op amp is fixed to the value that you wanted to have this node to be. So which I take it as VOCM, and you feed the output of this differential signal back to the VB value. Now, what are the requirements that is imposed on this extra op amp? So the first requirement is based on the precision at which you want this output node to have the common mode VCM to a particular value. Now, we have already seen during our class discussion, if we want the gain error to be around 1%, then we want this open loop gain of this particular amplifier to be around 1000. I guess you remember it. Based on the precision at which I want this common mode value to hang around, say for example VDD by 2, then we want this extra amplifier to have a very large DC gain, or the open loop, I can state it as an open loop gain in it. And the second requirement that is posed upon this extra op amp circuit is the bandwidth. So the bandwidth of my common mode feedback amplifier, okay, should have a larger bandwidth than compared to the bandwidth of our negative or the differential mode feedback network. Why did I state this condition? If I have a common mode feedback network, like the circuit that I have drawn in this, so this entire set of structure that I have drawn is nothing but it's termed as common mode feedback amplifier, and this amplifier should have a larger bandwidth than compared to the differential mode feedback circuit. So how does this requirement poses a kind of constraint to my entire design? So let us assume that if the common mode feedback amplifier were slow, like the entire bandwidth of this particular circuit is very small, and its basic function is to only provide a kind of DC biasing around this particular loop. And now that whenever it's a sudden spike, okay, sudden spike across any supply line, what happens is there will be a shift in the value of VOEs. There will be a shift in the common mode voltage by a larger quantity, right? And this shift has to settle back to this value, which is what we wanted is VDD by 2. And if this network has a very small bandwidth, then it takes a long time for us to reach back to this particular value, right? So that is what it happens here. So when I have the bandwidth of this common mode feedback amplifier, which is very narrow, then any spike would disturb my common mode output voltage to move away from this value. Say for example, from this voltage to somewhere down the way to 0.5 or something, right? And then this feedback would start working. Like it will try to work out in such a way, like it will try to bring back my potential from 0.5 volt back to VDD by 2. But the amount of time it takes to get back to this value would be very large. And if I'm not satisfying this condition, then what happens is the differential output that you are trying to observe out of this particular like by creating some kind of differential network like R1 and R2. So what happens is, like, if my differential mode feedback is higher or has a bandwidth that is higher than this common mode feedback, then actually what happens is, like, momentarily the gain of between the differential input to the differential output, the gain would be momentarily dropped, just because either my M1 to M1, M2 along with M5 might get into triode, or depending on how it has been shifted up, right? My M3 or M4 would get into triode. So now when any of these two conditions appear, obviously that the differential gain produced by this entire circuit, it would be reduced, and momentarily the gain from the input to the output for the differential signal would be disturbed, right? So that is the requirement that is being posed here. So we want always that the bandwidth of our common mode feedback to be larger than the value of the bandwidth of our differential mode feedback. And again, in general, I can state one thing, one more information. In principle, a fully differential circuit like this, like, simply I can state that it requires double the power consumption. Okay, it requires more power consumption than compared to our single-ended configuration. We talked about the loading effect due to this RCM, right? So in our discussion, so this loading effect due to this RCM, there are ways that are given in our textbook by which we can eliminate the loading of this RCM. I would encourage you people to go through those topics in the view of your interest. Hope this video would have given enough information about why we need a common mode feedback amplifier for a fully differential configuration, and we also have seen, like, how to build them, and then what are the important requirements that it needs. All of these things we have studied in this particular video. So in the next video, we'll be talking about the sleeve rate, which is an important large signal parameter. Thank you.